Okay, so in this video, we're going to talk about Fourier series, kind of in relation to LTI systems. Okay, so this video is going to kind of show us why we look at Fourier series when we're studying LTI systems. What do they get for us? Okay, so first I'm going to start by kind of writing something that should look familiar. Okay, so I'm putting in a complex exponential function, e to the j omega t, and I'm getting out that same function, e to the j omega t, times the frequency response, h of omega. So this was the eigenfunction property that we proved for RLC circuits. So usually I've been writing RLC circuits down here, okay, for the system, but now we're going to switch. Now we're going to transition into studying in more generality LTI systems. Okay, so from now on, I'm going to be talking about LTI systems where, of course, RLC circuits are an example of an LTI system, so that's a special case. But in general, there can be LTI systems that aren't circuits. So we're going to study things in more generality now. And we're still going to talk about this h of omega frequency response. And the frequency response is going to play a role by having this property be true for LTI systems. Okay, so when I put in e to the j omega t to an LTI system, I get out that same function times the frequency response h of omega. Okay, so I will write down something about this. So this eigenfunction, IO relation, input-output relation, it holds in general for LTI systems. And we will show this actually in more detail later in the course, but for now we're going to take it to be true. So we can kind of explain more of the things that kind of fit into the course at this point. We'll show this in more detail later in the course when we have more material available to us. Okay, but for now we're going to take it to be true. Okay, and we're used to it from RLC circuits. We're just now generalizing it to LTI systems. Okay, and we can use this relation to find the output of an LTI system when the input is a Fourier series. And I'm going to just write it as a sum. And I'll use x sub n, so maybe the signal is x of t, e to the j and omega naught t. Okay, so this is going to be the big reason why we study Fourier series, because for LTI systems, this property here is true. And actually using that property, as we'll see in just a second, you can find the output to LTI systems to an input that is in the form of a Fourier series. In other words, for periodic functions, we now have a way to get the output to a periodic function as an input to an LTI system. Okay, so let's see how that's done. So first of all, let's start with the property we have above, e to the j omega t goes into my LTI system with frequency response h of omega. And what comes out is just the same e to the j omega t multiplied by h of omega. In other words, the frequency response tells you how the system affects an input complex exponential at that particular frequency. How does it scale the amplitude? How does it change the phase? Okay, so what can we get from this? Well, look at the Fourier series. We have terms that aren't e to the j omega t, they're e to the j n omega naught t. So let's put that in, e to the j n omega naught t. What happens when that goes into an LTI system with frequency response h of omega? Well, again, I have to get the same thing out. All I'm going to do is in the top line, replace every omega by n omega naught. So I'm going to get the same complex exponential function out. And now what frequency should I look at my frequency response at? Well, the frequency of my input, which is n times the fundamental frequency omega naught. Okay, what else can we do to this? Well, let's just keep building up this Fourier series. Now we're going to multiply it by a constant, by that x sub n, that Fourier series coefficient. How does that change things? Well, by the linearity of this LTI system, when I multiply by a constant, I get the same output I got before, just multiplied by that same constant. So we're using the linearity property of this LTI system. Okay. So we're almost there. Now, finally, what happens if I put in my, I'll call it x of t, my whole Fourier series here? The big sum of all of these terms of the form x of n e to the j n omega naught t. What happens when I put that into the LTI system? What do I get out? Well, I'll call the output y of t. And again, if every one of these terms, I know what the output looks like. And when I sum them all up, I can use linearity again and say, oh, I'm just going to get a big sum now of the outputs of each of those individual terms that I already figured out. The big sum of x of n, h of n omega naught, e to the j n omega naught t. Okay, so this is pretty cool. We see now that for an LTI system with frequency response h of omega, when I put in a Fourier series, okay, I use this eigenfunction property to say, hey, wait a second, the output is also a Fourier series, so it's also periodic. And I actually know what the Fourier series coefficients are. These are my Fourier series coefficients. I'll call them y sub n. Let me just make a note. So the output is also a Fourier series. And it has Fourier series coefficients, y sub n, which are just the input Fourier series coefficients times the frequency response evaluated at that n, that subscript n, times the fundamental frequency omega naught. Okay, so this is kind of the big payoff. Without all of this, I would say, here's a periodic function, what's the output? And you would say, I have no idea, right? But now that we can put a periodic input into the form of a Fourier series, and we can use this eigenfunction property, we actually know what the output is. It's also a Fourier series, and we even know the Fourier series coefficients of our output. And it's a very simple expression here. Okay, so it's a really powerful thing, and we'll see the same thing hold later on in the course, even for aperiodic functions, for non-periodic functions. But that's when we get the Fourier transforms. All right, so let's do an example. So let's find the output to an LTI system, okay, with frequency response. And now I'm just going to draw this frequency response, okay, and it, it's in general for an LTI system, so it doesn't necessarily have to be from a circuit. And what I'm going to draw is actually a type of response, frequency response we're going to see often, and it's sort of an ideal low-pass filter, we call it. In other words, for these low frequencies, it equals 1, and then after a certain point, I'll label these as -3 and 3, the frequency response goes to 0. Okay, so the frequency response only ever equals 1 or 0. This is known kind of as an ideal low-pass filter. Okay, we're going to see things like this a lot in this class. Okay, so I'm just saying that this is the frequency response of some LTI system. Okay, and I want the output to that system when the input is x of t, and I'm going to use something we saw in a previous video, so the absolute value of sine of t. Okay, so we have an LTI system with that frequency response, and we want the output when the input is that function. And that function is periodic. We've seen that before. Let me just remind you. So from a previous video, okay, we saw that this function, absolute value of sine of t, we found its Fourier series. I think this was in the Fourier series examples video. Okay, and it was 2 over pi times 1 over 1 minus 4n squared. Those were the Fourier series coefficients. And then omega naught, if you remember, was 2. And so we get e to the j n omega naught t. In other words, 2j n t. Okay, so right here, these right here are our x sub n's, Fourier series coefficients of our input. And we want to find the output. So how can we do that? Well, again, in general, if I just came to you with the system and said, here's the input, find the output, it would be very difficult just from this expression. But we're going to use the Fourier series representation of that function in order to get the output very easily. And how do we do that? Well, look here. We know what the output Fourier series coefficients are. Okay? The output Fourier series coefficients y sub n are just the input x sub n Fourier series coefficients times the frequency response at n times omega naught. And omega naught here we said was 2. Okay, so this is just h of 2n. So we got to try and figure out what these coefficients are. Well, let's first look at what h of 2n is. We can see that h of omega is only 0 or 1. We want to evaluate it at all the even numbers. Where are the even numbers? Well, there's one at 0, and then we have 2, and we have 4, we have -2, -4, and so on. So we want to look at the frequency response at all of these points. And you can see, or maybe I'll put those back actually. So 0, 2, 4, -2, -4. Right, you can see that the frequency response equals 1 for those values and 0 for every other even number. Okay, so I'm going to write that down now. So this only ever equals 1 or 0. Okay, it equals 1 whenever that argument is between -3 and 3. Right, whenever the argument omega is between -3 and 3, the function equals 1 and equals 0 otherwise. Okay, but we just saw that what does this really mean? Because n is an integer, right? What integers can I multiply by 2 and stay between -3 and 3? Well, you can see from the picture or just by going through a few examples, the only integers that are possible are -1, 0, and 1, which would give us values of 2 times -1, which is -2, 0, or 2. Okay? So you can just, I mean, if you want, you can just do, this means -3 over 2 is less than n, less than 3 over 2, and since n is an integer, that means n can be -1, 0, or 1. Okay, so this means n is either -1, 0, or 1. And if n is anything else, then this frequency response is just 0. Right? 0 forever after. Okay. And so now we can figure out what our output Fourier series coefficients are. There's only 3 that are non-zero. Y sub -1, y sub 0, and y sub 1. Those are the only values that are non-zero, because everything else, this function here equals 0, and it kills those Fourier series coefficients off. So low pass filter is only letting through the frequency components in this range, and it's zeroing out everything else. Okay, so now we just have to calculate these. This is x of -1 times h of -2. -2. H of -2 is just 1. Okay, so this is just x of -1. And so if we plug in -1 up here for n, we're going to get 2 over pi times 1 over 1 minus 4, right? Because -1 squared is 1. So we're going to get -2 over 3 pi. Y sub 0 is x sub 0 times h of 0. Again, h of 0 is just 1. So I'm just going to get x of 0 here. When I plug in 0, I get 0. So I just get 2 over pi. And then finally, let me give myself a little room here. And then finally, y sub 1 is just x sub 1 times h of 2. Right, just plugging in right there. H of 2 is also 1. Right, that's how we found these Fourier series coefficients to get in the first place. And h of 1, well, if you look, the only time n appears is as an n squared. So whether I plug in 1 or -1 won't make any difference. So I'm going to get the same thing I got for x of -1, -2 over 3 pi. Okay, so what does that get me? Well, now I know that these Fourier series coefficients of the output equal those numbers, and y sub n equals 0 otherwise. All the other Fourier series coefficients are killed off by this 0 in the frequency response. So what do I get in the end? I can actually find my output. So y of t, okay, y of t is just going to be the Fourier series with these Fourier series coefficients. Okay, what does that mean? Well, that means I have 2 over pi times e to the j 2nt, okay? But n here is just 0, right? So I'm just going to get 2 over pi times e to the 2j times 0 times t. E to the 0 is just 1, right? So I'll just get rid of that. And then minus 2 over 3 pi, okay, for both of these, okay, times what? Well, for this one up here, when the subscript is -1, when I plug that in for n, okay, I'm drawing on x there, but look, the output is just going to be these Fourier series coefficients with the same complex exponentials as my input. Okay, so that's how I know that it should still be e to the 2j nt. Okay, so -2 over 3 pi. Now what happens when I plug in the subscript -1? I'm going to get e to the -2jt, right? Plugging in -1 for n. Plus, what happens when I plug in 1? I'm just going to get e to the 2jt. Okay. All I'm using here is that y of t, maybe I'll just write it down. I mean, we know this is the Fourier series for y. It's just y sub n e to the 2j mt. That's what we just proved here. Y sub n and the same complex exponentials as my input. My input had e to the 2j nt, and so my output has to have the same. Okay, so all I did was plug in for all these values. So when I plugged in -1, I get e to the -2jt. When I plug in 1, I get e to the 2jt. And when I plug in 0, I just get e to the 0, which is 1. Okay, so there's that coefficient times 1. All right, so now what can we do? Well, you can recognize that, hey, wait a second, this is Euler's, this is just, or the property we got from Euler's, this is just 2 times cosine of 2t, right? Cosine of 2t is this thing divided by 2. And so this thing alone is just 2 times cosine of 2t. So what do I get? I get 2 over pi minus 4, 2 times 2, over 3 pi cosine of 2t. Right, that 4 was this 2 times the 2 cosine of 2t. And so there you go. That is the output. So for this LTI system with that frequency response, when you put in the absolute value of sine of t, this ideal low-pass filter gets rid of almost all the frequency components in your input signal. It just keeps around 3 of them, 3 of these kind of frequency components in your signal, okay, 3 of these Fourier series coefficients. And when you actually construct the output, y of t out of those, you get this result. Okay, so you put in absolute value of sine of t into the system, and it turns out what you get is a cosine function multiplied by something and then with a constant added to it. Okay, so pretty cool. That would be a really tough problem if you didn't have the tools of Fourier series and what we know about LTI systems available. Okay, so we're going to be doing a lot more examples like this as the class continues. So I thought this would be a good example to show for now. But that's all I had for this video. I will see you in the next one.